Good morning, everyone. I'm Kshitij bohre from Acropolis Institute of Technology and Research, and I'm going to present my topic, direct volume data rendering, in front of you. So, what is volume rendering? In scientific visualization and computer graphics, volume rendering is a set of techniques used to display a 2D projection of a 3D discretely sampled dataset, typically a 3D scalar field. A 3D dataset is a group of 2D slice images acquired by a CT, MRI, or a micro CT scan. Usually these are required in a regular pattern, one slice from each millimeter of depth, and usually have a regular number of images pixels in a regular pattern. This is an example of regular volumetric grid with each volume element or voxel represented by a single value that is obtained by sampling the immediate area surrounded by the voxel. Volume rendered CT scan of a forearm. Here you can see the volume rendered CT scan of a forearm with color schemes for muscles, fat, bone and blood. Scope. So what is the scope of volume rendering? Volume rendering is distinguished from thin slice tomography presentations and is also generally distinguished from projections of 3D models, including maximum intensity projection. Nevertheless, epitomes of volume rendering models features a mix of examples, color and shading in order to create realistic and observable observations. Direct volume rendering. So what is direct volume rendering? A direct volume render requires every sample value to be mapped to opacity and a color. This is done with a transfer function, which can be simple ramp, a piecewise linear function, or an arbitrary table. Once converted to a RGBA color model for red, green, blue, alpha value, the composed RGBA result is projected on the corresponding pixel of the frame buffer. This way the way this is done is depends on the rendering technique. So what is volume ray casting? Using a simple camera model, the ray starts the center of the projection of the camera and passes through the image pixel on the imaginary image plane floating in between the camera and the volume to be rendered. The ray is clipped by the boundaries of the volume in order to save time. So here you can see how the volume raycasting works. This is furthermore explanation of that topic only. So here is an example of volume raycasting of a crocodile mummy. So splatting. This is a technique which trades quality for speed. With this means it focuses more on quality other than speed. Shear wrap. The shear warp approach to volume rendering was developed by Cameron and Undrill, popularized by Philippe Lacroix and Marc Levoy. In this, viewing transformation is transformed such that the nearest face of the volume becomes axis aligned with an off-screen image data buffer with a fixed scale of volume voxels to pixels. Texture-based volume rendering. Many 3D graphic systems use texture mapping to apply images or textures to geometric objects. Commodity PC graphics cards are fast at texturing and efficiently render slices of a 3D volume with the realistic interaction capabilities. Hardware accelerated volume rendering. Due to an extremely parallel nature of direct volume rendering, special purpose volume rendering hardware was a rich research topic before GPU volume rendering was fast enough. The widely cited technology was Volume Pro real-time ray casting system. So here it is furthermore explained. Here it's an example of mouse skull CT rendering using shear warp algorithm. Optimization techniques. The primary goal of optimization is to skip as much as the volume possible. Empty piece skipping. Often a volume rendering will have a system for identifying regions of the volume containing no visible material. This information can be used to avoid rendering these transparent regions. Early determination. This is a technique used when the volume is rendered in front or front to back order. Oak tree and BSP space subdivision. The use of hierarchical structures such as oak tree and BSP tree could be very helpful for both compression of volume data and speed optimization of volumetric rate casting process. Volume segmentation. Image segmentation is a manual or automatic procedure that can be used to section out large portions of the volume that one considers uninteresting before rendering. The amount of calculations that have to be made by a recasting or textures blending can be significantly reduced. So here you can see volume segmentation including automatic bone removal of the human skull using CT angiography. Multiple and adaptive resolution representation. By representing less interesting regions of the volume in a coarser resolution, the data input overhead can be reduced. On closer observation, the data in the regions can be populated either by reading from memory or disk or by interpolation. Pre-integrated volume rendering. Pre-integrated volume rendering is a method that can be reduced artifacts by pre-computing much of required data. Image-based mashing. Image-based mashing is the automated process of creating models, computer models from 3D images, such as MRI, CT, etc. Temporal reuse of voxels. For a complete display of view, only one voxel per pixel, the front one, is required to be shown. If an animation is needed, the front voxel to be shown can be cached and their location relative to the camera can be recalculated as it moves. Thanks. So here was my presentation on my topic. Hope you guys enjoyed it.